All right, let's be prepared to start the last talk in the morning. So it's a great pleasure to introduce you Professor Lino Grama from UNICA, CAMPINAS Brazil. That's going to speak to us about Milnor spheres via spherical T-duality and generalized log transform. Please, Lino.
Thank you, Leonardo. Thank you, all the organizers, for inviting me to speak here. It's a great honor. And this is a joint work with Leonardo Cavenaghi and Ludmil Katzarkov. And this is one of the works that is coming from this collaboration between the Institute with Latin America. And we started this, we call this approach to T-duality is to bone-net animals and matai, is in 2004. Is a T-duality for principal bundles joint with an A flux. It's a little bit different from the SYT T-duality used by non-linear symmetry. The intuitive idea is exchange, charge, and flux. Okay? We exchange in the principal bundle the two-form curvature between the three form that specify this flux. Okay, and this is the precise definition. We start with in a principal torus bundle over the manifold N, and a T-form closed T-form H on the total space E. Okay. And we call the dual bundle H check will be the T dual if there exists two form F, such that this is a invariant on the fibers, on the distortions, and non-degenerate on the fibers also. Such that this holds this formula here on the on this fiber space in the closed space. This is a fiber-wise space. And this concept of the T-duality, the first papers of this bone-net animals and matai prove some topological properties and KT properties, but I would like to mention some application in generalized complex geometry. This is introduced by Hitchin and developed by his student Marco Gauchelli. And this we can understand like a generalized complex structure as a complex structure of the double tangent bundle. And this generalized structure encompasses complex symplectic Poisson structure as particular case. And there is a very interesting.
You mean a complex structure on the bundle, or
sorry?
Do you mean a complex structure on the bundle or a complex structure on the total space?
On the total space of the double bundle, T plus T star.
So on the total space of the bundle, you have a complex structure.
Yes. Exactly.
Not just
almost complex also, if you can. It's an almost complex structure of the T n plus T star n.
Almost complex.
But the integrability is not with respect of the B graph, but this normal language. It's a different graph to guarantee the integrability. Because in the usual case, you have the T10, T10 black, this belongs inside T10. Right? It's evolutive. Okay? But
I don't understand the phrase, the interability is invariant. That phrase doesn't make sense.
No, I explain. Because if you start with an almost complex structure,
yeah,
you have this T1, 0 and the 0, 1. And this almost complex structure is integrable if this subordinate is evolutive with respect to the liberality. Okay? But in this case, the bracket is different. It's called Dorfman bracket or Kuhan bracket. That's the main difference.
Yeah, but what's the definition of a generalized complex work?
It's a endomorphism on Tm plus T star n such that G squared is the main identity. No?
So it's close to what?
Exactly, yes. It's an almost complex structure on the total space.
Without any further condition?
Yeah, this is an almost complex structure on in this space. But I talk about the integrability of this almost complex. I don't, is it clear or okay? And Cavalcanti Calciani gave some geometric interpretation. Can I say this compatibility of this T-duality and this generalized complex structure? And in some cases, we have the interchange between complex and symplectic structure. Okay? And then you can understand this like manifestation of mirror symmetry, if you want, in some setups. And then you can recover some well-known results from this, like the SYZ mirror symmetry, etc. Okay? By now, I would like to start. I back this in the end, this T-duality. But now, I would like to discuss about the spherical T-duality. We can understand this like non-abelian version of this T-duality, because now I'd like to study for principal bundles or bundles with the fiber is SU2 or the sphere S3. And then we start again with the definition due to Bognet everything in Matai. We start with bundles, ST bundle, and 7 homology class, 8 in the 7 homology class of the total space. And we, in some sense, emulate the definition between emulation of the T-duality, because the pair, the T-dual pair will be this bundle that P hatch from P hatch to N, such that we interchange the second chair class and of the two bundles. Namely, the second chair class of the P hat will be the push forward of the 7th homology class, and the homology class H hat is given by the second chair class of the initial bundle. Okay, we are interchanging this topological data, and this fitting this diagram, this square diagram like this. Okay, and also in the same order, the goal and everything on time, guarantee the existence of this spherical duo. And also we have some unities up to some topology with some elements in the H3. Okay, but in our case here, we are studying some 7-dimensional manifold. We have the total space is 7-dimensional. The fiber is a S3, is a 3-dimensional, and the base with 4-dimensional. And then we have no trouble with this. In this case, we guarantee the existence of the unities. And okay, at that point, there is we have this topological spherical duality. This Bognet everything in Matai and the other collaborators prove some topological results about this, KT, etc. But there is no kind of the geometric interpretation or more geometric realization of it. Okay? And in particular, there is no analogous to this Cavalcanti-Gautieri map to generalized complex structure, because this will be as an even dimensional, odd dimensional manifold. There's no structure to suppose. But now starting our work, and we for the rest of the talk, or most of the rest of the talk, we will fix on these Milnor manifolds. And let me recall the definition of the spherical bundles. Okay, a spherical bundle is called linear if the structural group is the orthogonal group acting on the sphere in the usual way, or in the equivalent way, the transition function of this bundle take values in the orthogonal. This is called linear bundle. And there is a bijection between the set of linear SK less one bundle over SL and the I L less one of SLK. And if you are taking a special case when K is equal to L is equal to 4, the linear bundles of S3 over S4 are parameterized by this element of pi 3 of SL4. And this is isomorphic to Z plus Z. In this case, given a pair of the integer numbers, I can build in a linear S3 bundle over S4. And these linear S3 bundle over S4 are usually called Milnor bundles. And very quickly, let's recall the Milnor construction of the exotic semi-sphere. We start with a pair of the integers, n, n, and build these maps from S3 to SL4. And this will describe explicitly the isomorphism between the pi 3 of SL4 and the Milnor bundle. We start with V, denoted quaternion, and then we consider this conjugation with the exponents m and n, and this t, n, and x you take values in SL4, and you need to apply some vector V. Okay? This is a linear transformation in SL. This is an element in the SL4, and this represents an element in the pi 3 of SL4. And now we can define this function f. Okay, this will be the boundary of the d4 times s3 and the d4 times s3. We have two copies of these, and this will be the gluing function. Okay, and then we arrive at the manifold n. This is the d4 times s3, two copies of d4 times s3, and we are gluing in the boundary by this diffeomorphism defined above. And okay, this is a very famous theorem. This gives rise to this Milnor bundle. Okay, this gluing gives rise to a Milnor bundle, and one of the very important theorem for Milnor is n, n is homeomorphic to S7 if and only if n plus n is plus or minus 1. But it's not diffeomorphic when n is equal to 2. Okay. This is the way to produce some we call Milnor sphere by gluing by the common boundary some diffeomorphism in these spheres. And then we have the complete classification of this phenomena when which n is a sphere or not. This is provided by using pi. And then let's denote this for k is the sum, n plus n. And c, k is equal to 1. We have this manifold is homeomorphic to S7. But Milnor defined this lambda invariant. This take this quantity, just involve these numbers in the constructions, m, k, n. And this is this invariant obstructive diffeomorphism. If this lambda is not equal to 0, we have a manifold that's not diffeomorphic to the 7-dimensional sphere. And then if you k is equal to 1, this number kn for n times n less 1 mod 7, this number obstructed this homeomorphism. Okay? And now we have our first contribution on this subject. That is, we can put this Milnor construction in the language of the spherical T-duality. Namely, if we start with a Milnor bundle and H flux here we will denote by this J is just element in 7 cohomology that is isomorphic to Z, and we have this following spherical duality diagram, and we remark that this there is a symmetry between these integers using because all numbers are integers n, k, j, and then so we would like to point out there is the symmetry between these numbers here in this diagram. And if k is equal to 1, we have this manifold n, 0, and j1 and j are homomorphic to S7, but not diffeomorphic if you have this invariant not equal to 1, mod 7. Okay? In this case, we can produce this spherical duality. We have some exotic object can be spherical dual. Okay. And just to remark, that if you take m is equal to 1, we have the usual Hopf fibration. And now I will look to put more structure here, because now we would like to explore more group actions. And very quickly, just to recall, now it's called Grama exotic sphere. This comes from group action. And to describe this, we consider this 10-dimensional manifold the group S2, given by S7 times we put inside the S7 times S7, and when the A, B, C, D are quaternions, and we start with this projection from SP2 to S7, just the projection in the first row of this gives rise to principal S3, sorry, there is a S3 action in the SP2, and the orbits will be this usual manifold S7. Okay? This is the usual projection, but Grama also considered another action. This is called style action, given by conjugation in the first pole, and the multiplication by on left to the second pole. And if you take the quotient of the 7 spheres, if you take the quotient by this action, we arrive in the exotic spheres, and this is called Grama sphere. Okay. This is another construction of the exotic manifold, but now we are using group action. Okay. And the ideas of Grama were extended in a general setup through a series of works by Carlos Duran, is a student of Grama, and Alcibiades Gigas is a work in the Unicamp also, and his students, Lorenzo Esperança and Leonardo Cavenaghi. And this given the formalism was named by star diagram construction. If you start with M in a G manifold, with the action, and pick the UI as a collection of G-invariant open sets, and then up to some adjustment, we can consider U action by G is equal to UI. And given two G-invariant sets, we denote by Uij the intersection. And then we have this definition. We call family of functions phi Uij to to G is a star collection if it satisfies some cocycle condition, and you have some invariance by the conjugation, equivalence by the conjugation. Okay, and that is another is a very important theorem. If we start with now principal G bundle associated to the star collection is a family of functions. At this point, we start with the principal bundle, and the principal bundle there is action of G. And then assume I can cover of this manifold by some special open sets, and there is some transition functions in star collection. If I have this star collection, then P admits a new action from the same group G at the beginning. We call star action, such that this is free, this new action is free, and commute with the principal action given at the beginning pi. The quotient of this new action is a G manifold, G equivalently diffeomorphic to this union, gluing by these functions, phi hat, where the action of UI restricted to the G action A, and the adjunct map phi hat ij is given by this form. Moreover, this pi together with the star action is a bundle, is a GG bundle, is a bundle with the principal bundle with respect to this action. What is intuitively what we have here? We start with the principal bundle with an action. Okay. This star collection tell me how to decompose the space in open subsets. Okay. And this theorem says this, I can glue this space by this quotient in a different way, such that in each open, this structure is preserved. But globally, this gives rise to a new object. Well, totally, possibly some topological, differential topology, different topology appear here. This encodes, because we start with the gluing those two disks at the beginning, the Milnor construction. And this is a kind of the formalism to encompass all this data. This decompose, including in some different way, this piece to obtain locally equivalent manifold or space, topological space, but globally different. And then we use this notation to denote this pi with the bullet action, this is the initial data, and the start action is in the horizontal arrow here. Okay, and just to remark, we can put all the Milnor manifolds, the Milnor manifold, the Milnor manifolds we can put in this setup with this start action. Just to recall, we start with this gluing D4 times ST2 cops by the boundary, by the diffeomorphism F. And we denote the Pn, just the n comma 0, 0 n, sorry. And each Pn is a S3 principal bundle over S4. And we consider two pairs of bundles, Pk and Pr. And we can see this as S3 bundle with the star actions given by this multiplication, conjugation, R in the left by R and the R bar from the right. And we can see the PR as S3 manifold with this following action. And this is the summarizing here. The total space of a given linear bundle can be realized as a star diagram. Okay, just this. And we have this important corollary. This just tells if you note this index R and K, we can provide a kind of shift on this space. Okay? And after this analysis of this star diagram, we can put the spherical T-dual in this language also. Namely, if we start with a pair of spherical T-dual pairs over S4, then there exists a S3 action fitting this star diagram. And the opposite is the same. If I start with the star diagram, there exists forms H and H hat such that the pair are T-duals. Okay. At this point, we have this concept, spherical T-duality, the star diagrams, okay, and these Milnor bundles. Okay? We have Milnor bundles, star diagrams, and the spherical duality, and all of you can put in the same language. And let's provide some examples. If we start with n, 1 comma n, comma 1 minus n, start with S3 principal bundle, Milnor bundle, and start with the H flux given by the integer number as a homology class. And we have seen this. This is a spherical T-dual, but we can go further, and some manifolds are not homomorphic to S7, but we can have some exotic structure. Like, for instance, if we consider n1, comma n, this is diffeomorphic to the unitary tangent space of S4, and we can put this in the spherical dual diagram, and we can arrive at this as a dual, is a dual to this exotic space here, Mj 2 minus J. And another interesting example is how the Grama exotic sphere appear in this dual. Can show that this dual to the usual sphere S7, but now twisted by this flux. This usual S7 sphere is a T-dual to the Grama, but now the Grama appear here with no flux. And then this will be kind of the twisted S7. Is it twisted by this homology class? And we can extend this analysis to the homotopy Hopf manifold. Homotopy Hopf manifold is a product of the odd dimensional sphere times S1. This manifold is a complex, non-simplex, etc. That is a sequence lectures in this conference from this subject. And if you set M is 1 less n, we have this manifold is homomorphic to the standard sphere, and we can I call it 8-dimensional homotopy of manifold is the product of some exotic S7-dimensional homotopy sphere times S1. Okay? And we can give some differential approach because the complex structure of this space was studied by Brisbane and Vandenberg. And we have some differential approach here to produce G-invariant complex structure on this homotopy space. And this is another remark here. If we start with the star diagram and see if M admits G-invariant complex structure, and prime also admits some complex structure. And now I talk about this another topic in the title, is a generalized log transform. Just to recall, the four-dimensional logarithmic transformation. We start with elliptic fibration, and then we can obtain a new manifold x prime from x by log transform on a regular fiber. If I take if the following surgery is made in this case, I take a tubular neighbor of the fiber and the glue at T2 times D2 via arbitrary orientation reversing diffeomorphism. So, and the absolute value of this composition is called the multiplicity of the logarithm transform. Okay, I start with the elliptic fibration, the fiber is a torus. I make some surgery, I remove the tubular neighborhood of this fiber and glue another disk times B2. Okay. And then some example, if I start with the Hopf, the usual Hopf, the four-dimensional Hopf, that is a elliptic fibration over CP1 over S2. It's given by the Hopf mapping the S3 factor and the S times S1, the fiber with topos. And then we have this disk decomposition, the straightening angles of this decomposition. This Hopf manifold we can obtain by this disk decomposition, where this gluing is given by this map here. This is encoded actually this Hopf map from the Hopf model. Okay. And apply log transform on this Hopf manifold. We just choose orientation preserved diffeomorphism from this 3 torus to for the 3 torus, and the plug here in this gluing. Okay, gluing by this new diffeomorphism. Okay, this is how we understand this logarithm transformation. And now we would like to emulate this to high-dimensional Hopf manifolds. And we start with the disk decomposition of the Hopf manifolds, this high-dimensional Hopf manifolds. And we produce the same surgery. We remove in a fiber in a gluing by oriental reversing diffeomorphism. Okay? Via these straightening angles. Okay? And the disk decomposition and the removal of fiber and gluing in the similar way to the four-dimensional log transform. Okay, and we are interested in the special case, and having a homotopy sphere times S1. Okay, just to remark, there is a sequence of papers for several authors. Hopefully, all here in the conference. It's not the same paper, but there's a lot of papers. They developed another approach to the Katzarkov, Lee, Lopez, Mathrm, and Berkowski. They developed a different approach to the high-dimensional log transform, and this is the to-do list to make the two definitions compatible. Okay, but this is on the way. And then just to recall this disk decomposition for the homotopy 7 spheres. Now we include this term S1, and this diffeomorphism here will be the we provide your log transform for some choose of the diffeom psi. And if I consider the sigma h, the smooth manifolds that are homotopic equivalent to the S7 plus S1 modeled out by diffeos, we have this following theorem. The sigma 8 is abelian, finitely generated group, and then the operation is the generalized log transform. Okay, this is a similar result to this homotopy 7 sphere, but now we can go from one sphere to another via this log transform operation. And for summarize, we can put all these concepts in the same diagram. Okay, and if we start with the homotopy 7 manifold with H flux, and then we have this following diagram. This we have this the usual spherical duality here, and our operation, we have this manifold times S1. This is homotopy Hopf, and we can go from one to another by logarithmic transformation. But this this line here, this dot line here, we can define this log transform via this spherical duality. This need to pass through this. Okay. And just to mention, we have some very intensive topological properties that's analogous to the four-dimensional case, like the nucleus, etc. It's very deeply connected with the singularity theory. Okay. But now I'd like to back to the first slide. And how connected exotic manifolds with T-duality, the beginning, the Thomas duality. Okay. This is based on joint work in Florence with Denis, Leonardo, and Ludmil. And now we consider the Cavenaghi manifolds, sigma for n as well. This is our boundary of parallelizable manifold. Okay, this is some, and this Cavenaghi manifold admits S1, a free S1 action, and the resulting quotient is denoted by sigma pc to n as well. Okay. And on the other hand, we can use this star diagram technique to produce another free action, another S1 free action on these spheres, S for n as well, such that the quotient is again this space sigma p c to m as well. Look, it's very important to remark here. This action is very strange. Also, this is just theoretical. It's guaranteed by the theorem because the original reproduced the regular foliation. But maybe understand this foliation in some microscopic very details will be very interesting. And now we have two S1 bundles over the same base. And our first remark in the declaration is these two bundles are T-dual, but now the fiber is S1, it's a one-dimensional columns. And this is in the sense of the first slide. We just exchange curvature and flux. Okay, the C1 represents the curvature of this bundle, and interchange with the tree form on the dual space. Okay, this is a quite a long computation, but we are arriving this. And this kind of the star diagrams in this kind of duality motivate us to propose some conjectures we are working out now on this. Now let's consider this Cavenaghi sphere now, not the manifold. And we can lift this star diagram to the cotangent bundle of the exotic spheres and the regular sphere. Okay. And we can make some careful analysis of the lifting of the isotopy classes of these exotic spheres. Okay, because this is all the game, all encoded in this isotopy class, how we're doing this boundary. And we can propose the following conjecture. These two cotangent bundles are diffeomorphic. Here is a worth to mention the basal work from Ludmil. That is In some cases, these bundles, these coordinate bundles are not diffeomorphic. When? What is the additional hypothesis? Here is these exotic spheres are not boundary of some parallelizable manifold. But the pervariant spheres are not covering this hypothesis. Maybe these are good space to test this. Okay, and this conjecture sampling is an important step to put more deep results because the dream will be if these two cotangent bundle are symplectomorphic. Okay, but this is a very beginning, but we are first working the diffeomorphic case. Okay, and that's it.